we had a talk from Lille, which is north of France, and now we are going to have a talk from Toulouse. It means that we have a balanced program, and so Nicolas will talk about theory, of course, many-body localization in a simple quantum spin chain problem. Okay, Nicolas, 30 minutes to allow some time for questions. And after 25 minutes, I more or less tell you that you have to think about a conclusion. Okay?
Good. Thank you very much, Alain, for the introduction. Indeed, I'm in Toulouse, but the weather is not so nice. So I believe probably it's like the average weather in France these days. Okay, so it's nice to participate to this nice workshop, even though, of course, we would have loved to be in Arcachon these days.
Oh, yes.
Anyway, yeah. So, so I will talk about theory and mostly numerical simulations on the many-body localization problem in a quantum spin chain problem. So let me first thank my collaborators on this project. Gabriel Lemarié, Fabien Allais, and Nicolas Massé, who is currently finishing his postdoc here in Toulouse, Laboratoire de Physique Théorique. So this is the outline of my talk. So first, I will give a brief introduction about NBL physics, and in particular, what are the interesting smoking guns to detect NBL physics. Then I will go to a recent work that we did, and I find it quite interesting, in particular in the context of this school, where a lot of topics were about Anderson localization. So what are the links between NBL and Anderson localization? Then I will go to a more recent work about extreme value, the extreme value statistics of the spin densities, which allowed us to have good signature or evidences for a Berezinski-Kosterlitz-Saulès transition for this NBL transition. And then I will conclude and summarize. Okay, so let's start with the model. So I don't know if this model has been already written during the workshop, but this is, let's say, the simplest quantum spin chain model, which is the so-called XXZ with the spin 1/2 with nearest neighbor interactions. And we also add this ingredient, which is a random magnetic field here, HI. And this is like an example of these random fields here in colors. Okay, so this model has been studied a lot by many people doing numerical simulations. And it's kind of universal because it also describes either interacting fermions, if you use the Jordan-Wigner transformation, or also hardcore bosons. And these quantum particles, like fermions or bosons, are now, instead of being in a random field, they can be seen to be in a random potential, HI. So before going to finite and high temperature, let me also mention that at 0 temperature, the physics is already very rich, and it has been discussed by Thierry in his talk. And here I show, for example, the phase diagram as a function of interaction delta. So delta is the interaction here, and the disorder strength in the vertical axis. And so we have this, this phase that Thierry discussed, where disorder is not sufficient to kill the superfluidity. So here I'm talking about in the bosonic language, okay, so superfluid. And but at strong disorder or strong interaction here, we have the so-called localized Bose-Glass regime. So this at 0 temperature is already a very, very interesting subject. But in the rest of the talk, I will move to high temperature for this problem. And okay, so let me introduce the problem. So now we simplify the problem and we go with the random field Heisenberg chain. Okay, so we have this model in a random field. So for this problem, the total spin is conserved, and so you can work in the sector with the SZ total equals 0, for example, which is the largest one. And even with this symmetry, the Hilbert space is still very big. And so you see that the curl n is the size of the total Hilbert space, and you see that it's essentially exponentially large with L, and L is basically the number of lattice sites, the number of spins, okay? So here I show an example of the many-body spectrum. This is from exact diagonalization, okay? So you see the spectrum. So here, this is the ground state, the first excited state. So you see here the level spacing is, let's say, of the order of 1 over L or 1 over L to some power. But then we are interested in this region, which is the middle of the spectrum, basically, where here the energy, the mean spacing between energy levels is extremely small. It's exponentially small. So this is a very difficult problem for many theoretical tools. And for example, if you are a numerician and if you want to do a full exact diagonalization and you want to study the property of these eigenstates, you can do a full exact diagonalization, but you're basically here limited to 18 sites, which corresponds to this size for the Hilbert space. So together with David Luiz and Fabien Allais, so we used another method, which is the so-called shift invert method. Okay, so the idea is just you shift your Hamiltonian by a constant sigma, okay, so sigma being, for example, this red line, and then you study the inverse of this Hamiltonian shifted, okay, and now this red state here at high energy becomes the ground state of this new Hamiltonian, okay, so now it's much easier because now there is a more separation of energy levels. And so then you can apply like usual technique like Langshaw's, for example, to study this high energy state. And with this method, we could gain, okay, it's not that impressive in terms of system size. It's the maximum number of spins is 24, but if you look at the Hilbert space, it's a 2 order of magnitude in terms of Hilbert space. So we could go up to 3 millions basically for this problem. Okay, so that was just a few of technicalities for the method. So let me now discuss what are the main smoking guns to probe MBL physics. So of course there are probably others, but I will focus on a few of them. So the first one is the spectral statistics, okay? And so the spectral statistics, a good tool is what is called the gap ratio. So you look at the ratio between adjacent gaps, so the minimum of the gap between level n-1 and the next one. Okay, so you look at this ratio, the minimum divided by the maximum, and it's known that this can probe the statistics, either random matrix theory at weak disorder here, and here for our particular Hamiltonian, this is the Gaussian orthogonal ensemble. Okay, so this gap ratio has this value, but at high disorder, the system becomes like the energy levels are not correlated anymore. So it's a Poisson process. And so we expect for the gap ratio to have the Poisson value. So 2 very different values. And these are exact diagonalization results for the quantum spin chain problem, where you see for different system size from 12 to 22, that there is indeed a transition between the 2 level statistics. So this is not only for theoretician, and interestingly, it has been, so this level statistic has been also probed experimentally in superconducting qubits. So this is the experiment of Rochon in Santa Barbara, and where they found, so here this is the distribution of the gap ratio, so they get different behavior at weak disorder, where they have GOE, and at large disorder, they have Poisson behavior. So another probe is, of course, the out of equilibrium dynamics, which has been discussed previously. So here you see the imbalance. So this is the experiment by Uli Schreiber in 2015, and you see that the imbalance, when disorder is strong, remain finite at long time as compared to weak disorder where imbalance vanishes. Another tool, which is quite interesting for numerical studies, is the entanglement entropy. So here I show results from Kemani and the group of David Hughes for another spin chain model, and they found, so here this is the entanglement entropy of a subsystem divided by the entanglement, the maximum entanglement of a thermal state. And so you see that there is a crossing which separates the volume law behavior at weak disorder, where the entropy is basically L, like the thermal entropy, and at strong disorder in the MBL regime, we have an area law. So the entanglement entropy is divided by the system size, just vanishes at the thermodynamic. So these are interesting probes for MBL physics, and so we use most of them together with David Luiz and Fabiale to draw this phase diagram. So here, this is disorder strength and the energy density. And so we found that there are indeed two phases for this model as a function of disorder strength. And also the critical disorder depends on the energy. So this is what we call the mobility edge between these two phases. And this, by the way, has also been observed in the same experiments. And okay, so here these are small systems of superconducting qubits, but they have also evidences for the mobility edge. Okay, so what are the open questions? So here I give just a small selection of the open questions for this problem. So a big one is about the critical properties. Okay, so about this mobility edge, for example, what are the critical exponents? What are the nature of the transition? Is it so? Recently, it has been said that it should be Kosterlitz-Serles. There's also recently many different numerical studies which don't agree on the value of the critical disorder strength here at the maximum. Okay, here we have 3.8, but some they can find something larger than 5. So there is like a bit of a crisis about this disorder strength. Another interesting open question is what about the link between the MBL phase and the Anderson localization on the random graph? So I will come exactly to this point now. Okay, so we like Anderson localization and we have a lot of tools, but can we study MBL using these tools? So the first thing we have to do is to rewrite our many-body spin Hamiltonian, okay, as a single particle problem. So you can do that because you choose, for example, a computational basis, for example, the spin basis, up, down, okay, the spin projection along the z direction. Okay, so now we have J, and J now are my sites. So I have an exponential number of these sites, okay, these new sites, they are basis states. And this Hamiltonian is just a hopping problem in this very complicated network. Okay, so now the hopping has just 1/2 because of this S plus S minus. So the spin flip now become integral of hopping in this Hilbert space. And I have a chemical potential mu J, which is pseudo-random. Okay, so let me explain a bit better that. So the complicated network, it has this kind of shape, and an interesting property of this network is the coordinates. And the coordinates, this is here a distribution of the coordinates in this network, and it's basically a Gaussian distributed with the mean value L/2. Okay, so it's a large coordinates network, and the chemical potential is given by this expectation value for each basis state J. Okay, so we see that this distribution is also quite broad with the variance which goes like H, the original disorder strength, okay, of the random field times the square root of L. So we have a coordinates L/2 and a disorder strength which goes like square root of L. Good. So can we do better with this? So we want to study eigenstate properties in this complicated network. And so to do that, we use like the participation ratio properties. So we first introduce the participation entropies like this, okay, with the P of J. P of J, this is just a probability to occupy the site J or for a given eigenstate psi, okay? So this Rényi participation entropy is just a generalization of the Shannon entropy or minus the log of the inverse participation ratio in the case of Q equals 2. So on general grounds, this participation entropy is expected to go like a prefactor dq times the log of the size of the Hilbert space. Okay, and this dq on general grounds is called a multifractal dimension. And there are three possibilities for that. Either dq is 1, that means my wave function is fully ergodic, okay? So that means my wave function psi occupies almost uniformly all my Hilbert space. And the opposite limit, if I am Anderson localized, dq should be 0. So that means SQ should be a constant, not growing with system size. And in between, I can have some dq between 0 and 1, and that means a non-ergodic multifractal behavior. So in a way, it's to say that still an infinite number of sites will be occupied in the Hilbert space, but it's only a vanishing fraction of the total Hilbert space. So I present now the ED exact diagonalization results for this participation entropy, okay, as a function of the Hilbert space size, which go from 1, okay, not 1 exactly, but small system size here up to the maximum system size, which correspond to a few millions in this Hilbert space. So here it's a weak disorder. At weak disorder, what we found something which is ergodic with a dq1. So these fits are log n precisely. But there is some curvature, but ultimately we can do a finite size scaling analysis of that, and we get a dq equals 1 in the weak disorder regime. On the other hand, for strong disorder, here h equals 5, we have something which is not localized, but multifractal. So here different symbols are for different values of q equals 1, q equals 2, and so we get a different slope, a different dq, which means multifractality, but more importantly, dq is less than 1. So we don't have any saturation of this participation entropy, so that means there is no Anderson localization in the Hilbert space. So let me summarize these findings. So here I show the multifractal dimension, dq, or general q, let's say, as a function of disorder strengths. And here we have the transition at HC. So what we have is full ergodicity at weak disorder in the ergodic regime. Then there is a jump of the multifractal dimension. The critical point as MBL properties is not thermal. And we have multifractality in the MBL regime and no Fock space localization, as for example, we can read in some literature. There's no localization in the Fock space. Interestingly, we find that the multifractal dimension is going to 0 slowly, like 1 over the disorder strengths, 1 over h. And so the next question is, how can we understand this multifractal behavior and the 1 over h behavior at strong disorder? So to do that, the first thing to do is to do like a naive, strong disorder decimation. So let's go back to real space. I write again the Hamiltonian, okay, and here I assume the disorder distribution, okay, this is a box for my random field, is very broad, okay, between minus h and h. And so if it is very large, I would say, let's take a cutoff of size gamma, okay? And I say that if the field at a given site is extremely strong, it's quite likely that the spin will not fluctuate. So I will freeze out these particular spins where the fields are very strong, okay? So I do that, I decime them out, okay? Okay, so these yellow arrows are now frozen spins. They can be in or opposite to the field, of course, because I am at high energy. And then in perturbation, there are like effective couplings above this. But more importantly, the number of active sites, the one which can still fluctuate, has been strongly reduced. And the number of active sites is here. It's reduced by a factor which corresponds basically to the area, to the red area. So, and this factor is gamma over h. Okay, fair enough. So that means the active part of the Hilbert space is strongly reduced using this decimation scheme. So I have a large number of frozen spins. Okay, and this is the typical eigenstate. And only n active sites which have still some fluctuations like this. So the active part of the Hilbert space is reduced by a power gamma over h. Okay, so now in this very simple scheme, if you want to compute the participation properties, it's just the log of the number of active sites in a simple point of view, and so you get something like 1 over h times log. So from this very simple argument, of course, we don't have the right number in front, but from this very simple spin freezing argument, we understand why when you increase disorder, you have less and less and less sites which participate to the wave function. Okay, so can we go further and understand if this spin decimation is really justified or not at strong disorder? So now I show you some exact diagonalization results for the magnetization. Okay, so now this is the expectation value of the local magnetization at infinite temperature. Okay, P of mz, a function of mz, so this is between -half and 1/2. So at weak disorder, what we have a distribution which, when you increase system size, become narrow and narrow, and so it's peaked around 0. And this is what we expect at infinite temperature, that the spin can fluctuate between plus and -half, and on average it will be 0. But if you go to strong disorder, this is the situation. This is the ED result for the distribution of magnetization in the spin chain. So you have a U shape like that. And it's very interesting because now we can define what we call delta, the deviation from perfect polarization. So this is 1/2 minus the absolute value of SZ, okay? And these tails here are power law tails, okay? So it diverges with the power law. So from that, we can apply extreme value statistics. So it's a very simple argument for given such a distribution with a power law tail, on a given sample of size L, what is the minimum for delta? And this minimum is related to the power alpha like this. So the minimum should go like the system size to a power -1 divided by 1 minus alpha for the most polarized side. Okay, so let's go now to this most polarized side and look how this, so this is the delta minimum, and we take the typical value average over many disorder realization for different disorder strengths as a function of system size. So you see here very different behavior. At small disorder in the ergodic regime, we have seen that all the spins should go to, the expectation value should go to 0 at our system size. So that means that this delta minimum is going to 1/2. And this is what we observe here. There's a small crossover and it is going up and it will go to 1/2 here. Okay, like that here. But then in the MBR regime, we have some frozen sites, okay? And SZ will be plus or minus 1/2, not exactly frozen, okay? But we see that this delta minimum is going to 0, like that, at strong disorder, and it's going with the power law, L to the minus gamma. So it's going to 0 at large size. So that means that we expect chain breaking at the thermodynamic limit, a bit like in the Kane-Fisher problem. There's chain breaking in the system. So that means my spin decimation is well justified, in fact. At the thermodynamic limit, that will be the physics. Some spins will be completely frozen and the chain will be broken. Okay, so what can we do with that? So let's analyze this exponent gamma that I call the freezing exponent. So this is how it goes as a function of disorder strength. The freezing exponent gamma, so here it's basically 0. So these are some oscillation of finite size oscillation, but it will be 0. And it's finite in the MBR regime. And there is this behavior here. I will come back to this behavior in a minute. So before that, let me rapidly discuss some analytical understanding for the spin freezing. So let us start with free fermions, okay? So we can easily diagonalize the free fermions with new orbitals, okay? With new operator Vk, and this phi ik are localized orbital. Okay, and we know that at strong disorder, the localization length is going like 1 over the log of the disorder strength. Good. So now let's go to many-body. We don't put interaction yet, but let's go to many-body and put L over 2 fermions, okay, L over 2 orbital out of L sides, okay? So this is a sketch of that. And let us compute the density, okay, which is related to the spin density in the spin chain language, okay? So the density will be just the sum of occupied orbitals, okay, like that. But I will have a maximally occupied site if, by chance, I have L max consecutive orbitals close to each other. For example, like this, where I have 5 orbitals close to each other. So then this is at this side, at the central side, that I have an N max. The maximum occupation will be here at its red side. And this is the sum of exponentials. And we can work with that. And this is simply 1, which is the maximum occupation, minus some correction due to N max. Okay? And interestingly, in a chain of size L, so it's like if I do if I flip a coin and if I want to say, okay, I do that 1,000 times, and what is the longest list of tail, for example? Okay, so if I have L of this drawing, the longest will go like logarithm of L. And precisely here's log L divided by log 2. So now if I plug this L max in this exponential factor here, I get immediately the power law behavior for delta mu. L to minus gamma, and this exponent gamma is related to the localization length, like that, 1 over xi. And this 1 over xi should go like log h. And this is precisely what we get at strong disorder. Indeed, this gamma is going like log h. Okay. So we can now, so that was free fermions. We can now add interactions, but I think I will skip this part because it's a bit technical and I am a bit out of time. So we can add interactions. Okay, and at the end, what we get is that even in the presence of interaction, we expect this exponent gamma to be directly proportional to the inverse localization length, and more precisely, the typical localization length. And this is an important object. So before going to the scaling analysis of the problem, let me just show that we can numerically see this phenomenon for...
You know that you have only 2 or 3 minutes, okay?
Yeah, okay. So for different disorder strengths here, you see that, so let's focus on the strong disorder. This is the magnetization as a function of the sites for one particular sample. And you see that the most polarized site is indeed in the middle of here it's not occupied, it's basically empty orbitals, but this is exactly the same mechanism, you see. So we have the spin down here, and the maximum will be in the middle of such a small subsystem. So we can do scaling analysis for this quantity. Okay, and so basically what we have to retain here is that there are 2 parameter scaling, so in the delocalized regime and the localized regime, okay, with different, so here this is a volume law scaling, where this is the Hilbert space size, which is divided by what we call the non-ergodicity volume, lambda, where in the MBL regime, we have a factor lambda, which is related to a typical localization length. So interestingly, the best collapse is obtained for disorder strength, which is a bit higher than what we found previously, for example, using the gap ratio, something close to 4. But this is not fundamental what this number is. Interestingly, so the non-ergodicity volume diverges close to the transition, and the MBL length scales also diverges. And what is interesting is the way it diverges. It goes with an exponent 0.5. Okay, and so I don't have enough time to explain that, but recently there are various groups who promoted the Kosterlitz-Saules mechanism for this transition. And what is more important, that they found that the typical length scale has this singularity here at the transition with the square root singularity. And our data perfectly agrees, given the fact that our freezing exponent gamma is related to the typical localization length goes like the square root. So this is in perfect agreement with the Korsavy-Sauer scale. Okay, so I will skip that because I don't have time. And now let me summarize.
Good.
Okay, so basically I discussed 2 points which are strongly related. The first one was what is happening for the MBL problem in the Hilbert space, and we found that there is a strong difference between the delocalized phase where the wave function are fully ergodic and the MBL phase where there's no Fock space localization, but rather it's a multifractal behavior with a multifractal dimension vanishing like 1 over the disorder strength. This can be understood from a simple spin freezing mechanism, and this spin freezing is indeed at play in the problem, where we found that there are chain breaking in the system with a power law behavior. Okay, for this chain breaking with an exponent gamma, we can understand that using this simple analytical description with free fermions, and our exponent gamma agrees perfectly with the Korsavy-Sauer prediction with the gamma 0, a jump at the transition, and here a square root singularity in the MBL regime. So with that, I want to thank you for your attention and ready for questions.
Okay, thank you, Nicolas. It's really very clear, even for a poor experimentalist like me.
Very good.
Yeah, sure. Questions. Come on, Antonio.
I think
there is
Thomas,
a question in the chat.
Thomas has a question.
Okay.
Yes, I can start.
I have not seen
maybe something I'd like to understand better. Just at the beginning, you showed a phase diagram from ergodic to MBL as a function of energy density.
Yes.
So I'm just curious, does that mean, so it seems really reminiscent of like standard Anderson localization where really above a certain energy, everything is localized and below everything is unlocalized. But could you imagine a situation where you have a state with really high energy, for example, which is localized, and another state with same energy would be not localized and going to ergodic then? Like, does it seem obvious to you that the energy really is the only quantity? Like, for example, we have seen like in this quasi disordered system, sometimes at the same energy, you can have localized and unlocalized state and not localized state. And I wonder whether here in this complex situation, that's not obvious to me that only the energy can matter.
Well, okay, I'm not sure to completely understand because, okay, so here the energy is a good quantity for us, and so yeah, the total, because yeah, here again, the thing is, this is the total energy of the many-body state. Okay, it's not like having an individual single particle state with different.
But you could have, let's say, you take a quantum state with a given energy, and this one can be either in the ergodic regime and go or not. I mean,
yeah, what I believe is okay. Yeah, something interesting regarding that aspect is okay. So I didn't talk about that, but here in the ergodic regime, the out of equilibrium dynamics is a bit complicated. It's a very slow dynamics, and it's not completely clear how it relates to ergodicity. And possible understanding of that is you have a system, and locally, the local, if we can, I don't know how exactly to define that, but locally the energies can be very different. You could have some hot or cold small subsystems. And so some of them could localize while the global system should not, something like that. And that could explain why there are some subdiffusion. So here, so most of the study, they found some subdiffusive regime. And even at weak disorder, in fact, even here, that could mean because, yeah, you could have some particular disorderization or some particular subsystems in the full system which are, let's say, at smaller energy or higher. Because okay, here you see it's cut. Of course, it's should be between 0 and 1, but numerically it's more finite size effect here. But we should have something going to 0, but we don't know precisely how it goes to 0 like that, because the critical disorder in the ground state is 0 precisely. Okay, so I don't know if it answers your questions. Your question.
Are there other questions?
There is one in the chat by Nicolas Laforencie.
Yes, Nicolas.
Merci Thierry.
Yes,
surveiller.
thank you very much for this nice talk. I have a very naive question just to be sure I understand the terminology. So you showed that in the MBL phase, the states are actually multifractal. So they are not localized, but still you call the phase many body localized phase. So I fail to understand this difference. And also at the critical point you wrote on your graph, this point is MBL. What do you mean this point is MBL?
Okay, so the terminology, like very often, terminology should evolve with time. But yeah, many body local. Okay, in many aspects, many observables, the system is localized.
Transport, you mean, for example?
Yeah, there's no transport.
Okay.
The eigenstate property are just uncorrelated in the spectrum. Entanglement is very low.
Mm-hmm.
So, yeah. So in many aspects, this is really an insulating high energy. But of course, yeah, then you could say, what are the links with Anderson localization on the graph? But of course, this depends on where, in which computational basis you study the problem.
And when you wrote at the critical point is MBL. This is what is written in your. What do you mean?
What I mean, okay, because there were a debate at some point asking, for example, I mean, if you want to study like with usual finite size scalings, so usually people try to find quantity which cross at the transition.
Mm-hmm.
And at the transition,
okay.
It could have a particular behavior, a critical behavior with some power or something like that. Here, so the consequence of the fact that the critical point has all the property of the MBL phase is there will not be there are no crossing at the transition.
There's no crossing. There's a singularity. Yeah. Okay.
Yeah. So, for example, if you look at the gap ratio, a lot of people they try to look at the crossing here. I don't know if you see the plot here, but in fact, the critical point should be Poisson.
Mm-hmm.
So
yeah. Okay.
crossing should drift down, and it's also drifting to the right. Okay, and down. So, and the gap ratio at the thermodynamic limit should be Poisson and jump. Should be GOE and jump to Poisson, and no intermediate statistics. Okay, that's the main conclusion for all this. Yeah.
Thank you.
Okay, if there is no very urgent question, I wait a few seconds. Okay, I think
Marcel has a question. Sorry to intervene again.
You want a question, or you want to conclude, Marcel?
No, I just raised my hand for a question.
Okay.
Okay,
so,
but you can ignore me. That's your right
I
as a chair.
I cannot ignore you, Marcel.
Okay, I have a question concerning one of the last slides where you see the freezing, the localization of state depending on the disorder strengths.
Yes.
So the one where you have all the one going up and okay, this one.
Okay.
Okay. If you look at in the middle of the like the purple ones, you see that it goes down and then a bit up after, and this point seems to move. If you look at the point that are a bit above the light blue or the purple above, you have this change of behavior, but a bit before in terms of system size. Why don't you? You seem to rule out the fact that the same thing could happen, but for larger system size, like for the red points or the greens, you could have something going down and then up after a given.
You're right. You're right. But yeah, okay. So looking at that, it's impossible to conclude. Basically, to say, well, the critical behavior is somewhere here. It's impossible to conclude completely. So the first thing, okay, we could try to fit on small, let's say 3 or 4 points, and take this window and move the window. And this is what is done here. Okay, it's not completely conclusive. Where is the transition point? So we had to do a more quantitative analysis of these numbers of this, and this is the scaling analysis. And this scaling analysis, so in a way, this is thanks to Gabriel Lemarié, who did that. He's really an expert now on doing like the scaling function, and there's no assumption on that. There's no assumption. So it's not like, oh, I see this point, it seems to go up a bit. No assumption. So you try all the possible HC and try to get what is the best collapse. And I tend to believe that this is today the most professional way to try to locate the critical point. And on top of that, if I come back to this, so here it's not clearly visible, but the effective exponent here is, for example, a strong disorder is increasing. Is increasing when we slide to the right. Okay, so it goes this way, but this doesn't happen here. Here it's always going gamma. So the effective gamma is decreasing. It's going to 0, and it's even changing sign here.
So you're looking at the curvature.
Yeah, so so in a more, let's say, a human way, not computer way, because the scaling analysis, this is really a computer which does this. It's like a big data problem, okay? You have a big data problem, and then you do some polynomial feeds of this and try to get using these 2 scaling functions. It's controlled, but a human couldn't do it, I would say. Whereas here, we have something which is more sensible for us, which is what is the curvature of that. And this is what you see here, basically. Okay. So when you increase system size, the effective gamma is increasing. So for sure, this point here, the effective gamma, when you increase system size, is going up. And the fact that this is going up, for me, this is a clear evidence that gamma is, we are in the MBL regime. The critical regime is much more difficult to understand, and that's why we need this more sophisticated scaling analysis. But you saw our critical point declared is 4.2 with an error bar of 5 on the last digit, which is big, and this is the best we can do. So error bar of 5 means it could be up to 4, almost 5. So this could be here, the critical disorder strength. So another lesson of this problem is it's extremely difficult to get the right number of the critical point, while the universality class seems to be more robust in our analysis.
Okay, so I will start again to conclude. Thierry Jamarki à tout le monde. Okay, so Thierry, you want to add something? Or?
No, I was trying to answer a question that was asked before to everybody, so I thought, why not answer? So this was.
So there is a parallel session.
Yeah, there was.
So it's difficult for me, because I have to look at the chat, to look at and to control the time. And so I think that, well, maybe if you want, you can continue to discuss, but I think it would be more reasonable to declare the end of the session and then to pass. So thank you everybody, because the assistance is really impressive and everybody was there. It's beautiful. In a sense, I can propose that if you want to continue to discuss once the session is finished, just stay. And hopefully the session will not be closed and people who want to continue to discuss. But meanwhile, I will pass the speech to Thomas, who was organizing this Arcachon symposium or school. It was a school. And I have to thank all the speakers who really respected the spirit of a school, which is to be as pedagogical as possible, within the time which is allotted. So Thomas, so thank you everybody for this session this afternoon, and Thomas as a general chair of this Arcachon Symposium.
Yes, so just short conclusion. So it's essentially, I'd like to thank the people, essentially thank the other organizer, Pierre. It was, you know, all the mess with this rescheduling, and but not too bad in the end. I'd like to thank also the people from the Simon Foundation, Catherine and Ray, who helped quite.
Yes, the team in Minnesota. Yes, they are really efficient. Thank you very much for all you do.
Really makes the organization a lot easier. I'd like to thank the speakers, like Anna said, for their pedagogical lectures. And I hope all the participants enjoyed it and learned a lot on the subject. I did myself learn a lot, so I hope this is the case of other participants. And obviously we had to do it remote, so we missed all the coffee breaks, all the informal discussions. That would have been great. So hopefully we can meet on better days. We can really travel and maybe visit Arcachon once.
Yeah, there will be other schools. Yeah.
Well, let us dream that when the virus is over, and let us dream that this network, Simon's network, lasts long enough for we can organize another school, and why not in Arcachon?
And then, well, the good thing about that is there was remote, that we had people from New Zealand to US and Brazil and whatever. So, so even if you know, many of the initial registered people were from France because of the sanitary conditions, but in the end, we had people all over the world who could attend. So this is a beneficial aspect. So like, thanks again, all participants, and bye-bye, everybody.
Thank you.
Bye-bye.
Bye.
Bye.